Alright, we have a little warm-up right here. There are 4 of them. Please do these questions. So pause the video, give them a try, and then see what you guys got. So let's go over the first one. So we first take the derivative, but this is going to be implicit differentiation because we have x and y's on both sides. When I take the derivative of a sine, that would be a cosine. And the inside we're going to keep the same for right now. But because of the chain rule, we also have to take the derivative of the inside. The derivative of the inside would be a product rule. So it would be the derivative of x times y plus the derivative of y times x. Now when you took the derivative of y, you must attach y prime. And the only reason is because they asked for dy dx. Had they asked for dx dy, you would do the exact same thing but in reverse. X's would give you an x prime. And then the derivative of x is just 1, giving us this. So over here, in a much smaller font, I did it again. I kind of distributed the cosine, and then the 1 just remains the same. I obviously wanted to keep this by itself because that's the one that has the y prime. The y prime was the important guy. And moved this to the other side. Then I divided by x. I tried to get rid of the x and the cosine of xy. So I divided x cosine of xy on both sides. Now we have a dy dx. Y prime, otherwise known as dy dx. Alright, that's the first one. Hopefully you took good notes on that. Let's do the second one now. Alrighty, so for the second one, we're taking the derivative of this guy, bless you. And when you take the derivative, we have to consider the fact that we're taking the derivative of a function that has a function inside of it. So that's going to be a chain rule. So the derivative of f of x is just f prime by you plugging in the natural log of x. And then the derivative of x natural log of x is just 1 over x. So we're going to end up having to do something like this. Because this was on the outside. It's not like first find the derivative of f and then do natural log. They want to know what the derivative of f of natural log of x would be. So you have to consider the chain rule. So first thing, find f prime, which would be 2x plus 2. Plug in your natural log, which would be right here. And then attach a 1 over x. So that would pretty much be the derivative. Of course, you want to probably simplify that a little bit to make it look nicer. Actually, this is probably as nice as it's going to get. There's not a big benefit of having putting that in there. Alright, so that would be it. So that's the derivative. And then now we do number 3. Give that a try, or you already did. So let me just go ahead and do it real quick. Alright, so I changed 1 over x squared to just x to the negative 2. Added 1, divided by it, so it's 1 over negative 1, and then x to the negative 1 plus c. So the answer would be D. D would be the right answer. And then for the last one, number 4, you have to just do each integral separately. The antiderivative of sine is negative cosine, but I have to account for the 2x, which is why I'm going to attach a negative 1/2, because I want to cancel out the negative and the 2 that I'm going to end up getting if I was to take the derivative of cosine of 2x. So this derivative, if you just want to double check, would it go back to this? And yes, it would. Same thing for the cosine. I want to have a sine of 2x. But because I'm going to end up getting a 2, which I didn't have right here, I'm going to have to attach a 1/2 to prove that. And then, of course, don't forget your plus c. That's it. Let's move on. Alrighty, so we're going to start a lesson. This is a very short slide right here. I'm not going to talk very much about it. But when you have a number raised to x and you're trying to take the derivative, it's just going to be the base to the x times natural log of the base. So if you had 2 to the x, it would be 2 to the x times the natural log of 2. When you do the integral of that, then it would be the same thing, but you divide by natural log. So if you had 2 to the x and you're trying to do the integral, it would be 2 to the x divided by natural log of 2. So for the derivative, you multiply natural log. For the integral, you divide by natural log. So the only note I want you to put right now is this right here. This general rule. Alrighty. So this is really all you need. I don't know why I also selected that. This is all you need right here. Alrighty. So we're doing an integral of 2 to the x dx. Now, you don't have to do the derived way of doing it that they do, because you can just use the shortcut that we talked about. So if you have a 2 to the x dx, it's just 2 to the x divided by natural log of 2. If you were looking for the derivative, it would have been 2 to the x times natural log of 2, but we're doing the integral, so you just do divide. Alrighty, over here we have a integral of a tangent, which you can change to a sine over cosine, and given that we already know that the sine and cosine are integrals of one another, meaning the integral of the cosine would be sine, and the integral of the sine would be negative cosine or whatever, we can go ahead and do the u substitution. So in this case, let's let u equal cosine, so we're going to end up getting a 1 over u, but because you end up getting a du needing a negative sign, we're going to have to attach a negative, like in front of it, not in front of it, just like somewhere, because the negative has to be accounted for. So the negative is just pulled out. This ends up being du over u, and then the integral of that would be just the natural log with an absolute value, given that u cannot be negative inside. The inside of natural log cannot be negative. And that'll be it. So pretty much we would end up having this right there. Of course, you can mess with the natural log properties. For instance, the natural log of the number in front of a natural log can become a power of the inside of the natural log. In which case, you would end up having a natural log of cosine to the x, cosine of x to the -1, otherwise known as secant. So you could have this as well. So either one would be fine. I assume most of my students will stop right here and not go through the trouble of making it a secant unless told to make it a secant. Let's move on. So, same thing with the secant. If you have a secant, it's probably good to kind of change it up a little bit. Over here, we essentially are multiplying secant by secant x, tangent x, top and bottom. Because the reason why you do that is to end up with this bad boy right here. We know how to deal with it, because if you let u equal secant tangent, then the derivative would be secant squared secant tangent of x. So we can essentially do a u substitution. There's a lot of work missing right here, so let me just go ahead and write down so you know what I'm talking about. The integral of secant isn't clear, but there's a mathematical trick. If you were to multiply by a fraction where you have secant and tangent on top and bottom, you would end up getting essentially what it shows right here. You would get this. You want to combine the top, and then the bottom is right there. And if you let u, oops, that looks like a y. If we let u equal, and then the denominator, secant of x plus tangent of x, you conveniently would end up getting secant tangent. So I'm just going to put st for secant tangent, plus and then secant squared. That's the exact same thing that you have right here. So that would be dx, by the way. So du would be all of that dx, which is exactly all of this. So essentially you would end up with 1 over u du, and that's just natural log of u plus c, and you just plug that back into right here. That's how they ended up with this answer right here. Of course, you must maintain the c, so make sure you have a c there. All right, let's move on. That was a that was an easy one, but at the same time, you had to know this trick in order to do it. Most people probably would try something else, maybe turn this into 1 over cosine and see if you can do something with that. But essentially, this trick will work. So just make sure you have that in your notes. So here's some shortcuts. The integral of sine is negative cosine. We know that. We know as well. But when it comes to tangent, cotangent, secant, cosecant, these are the integrals. And you probably would think that this is probably a lot of fun doing them, you know. Essentially, it's the same trick where you try to have a fraction and then let the bottom equal u. But the fraction has to be something when you take the derivative of the bottom, it will give you the top. Kind of like what we had in the previous few slides. So these are some identities that you should probably write down in your notes just to have. There we go. That bothers me if I don't color it in. There we go. Alrighty. So let's do these problems. So pause the video and give these a try. So I did the first two, and I'm going to leave the last two for you to do. Essentially, we took the derivative. The shortcut is it's just going to be the same thing as the function, but natural log of the base. So 7 to the x power times natural log of 7. When you do an integral, it's the same thing, but you divide instead of multiply, and then you attach a c. So go ahead and give these two a try. And then I also want you guys to try this right here. Now, I will do two of them, and let you do the other two. For the first one, cotangent is just the same thing as cosine of x over sine of x. And then you're pretty much going to let u equal to sine, and du will give you cosine of x. This is actually going to be a much better integral u substitution than the one we did before with the tangent, because we don't have to worry about a negative. So that one's going to be quite easy. So you should be able to do this problem. I want to talk about this one a little bit. I think it's better if I talk about this, so you know what my thought process is. Essentially, I'm going to multiply it by a fraction, but the top and bottom is going to be the same thing. But I want to multiply by something that will allow me to end up doing a a derivative, that will be the same as the the top. So since it's cosecant, I'm probably going to be looking at cosecant of x and cotangent of x. And more specifically, probably, for right now, let me just go ahead and write down cosecant of x plus cotangent of x, just like we have with the tangent. I'm a little worried about that I might need a negative, but again, this is just to kind of try out what it would be if I did that. So if I did this, I would clearly let u equal cosecant of x plus cotangent of x. When I take the derivative, I would end up getting, that would be negative cosecant of x cotangent of x. I like that a lot because I'm going to be multiplying the cosecant times the cotangent. And cotangent would be negative cosecant squared of x. So virtually the same thing. I mean, probably end up needing to factor out a negative. Essentially what that's going to be is negative and then all that good stuff. Cosecant of x plus cosecant of x cotangent of x plus cosecant squared of x dx. So when I actually plug it in, I will probably end up putting a negative right there. That will allow me to have a 1 over u, so negative integral 1 over u du. So my answer would be negative natural log of whatever u equaled. So pretty much, let's see, all of this good stuff, plug it into right there. Alrighty, so the other ones follow the same suit. You just have to use these tricks. For number 7, want to do something similar to what I did right here. And for number 8, we actually did that problem already in the previous one. Just do it again for fun, which is when you would change it into sine over cosine. Alright, see you guys tomorrow.